Hello students, welcome back. Now let's go to section 4, Hypothesis Testing for Population Means 2. This time we are going to study the case where we don't know the population standard deviation sigma. Here's a reminder, the checklist, and we're going to be typically on the t distribution here because we don't know sigma value. And here's a reminder on this t distribution. Students' t curves come with something called the degree of freedom, and for our purpose, the degree of freedom is n-1, sample size minus 1. We saw that behavior for sample standard deviation computation, and again here, and that's always the case for one-dimensional statistics. Now for higher dimensional cases, you may have some n-2 for 2 dimension and so on, but all those are for upper level. So here, we have degree of freedom, which begin with 1, which means sample size is 2. And we have the z-curve in red and the t-curve in blue. All right, from degree of freedom of 1, let's increase the sample size. Increase. And as you can see, the blue curve, the t-curve, approaches the z-curve. In general, if you have a sample size of 100 or more, then typically we'll just use normal. We'll say they are the same for any practical purpose and just go ahead with it. Less than 50, then you're going to use t-distribution. Now between 50 and 100, t-distribution is better, but it's a kind of gray area. By the way, here is a summary, basically. The mathematical structure of hypotheses, remember, and important sample statistics, sample size, sample mean, and sample standard deviation. And mu0 is for the null, the population mean for the null hypothesis, and the significance level. They are not coming from the sample, and they are coming out of nowhere from the problem itself. And then we can visualize the critical value method like this. So this program is randomized, so just run it over and over again, and as you can see, given critical value, if your observed mean is close enough to the null, so if it falls in the blue region, then null wins, and then if it's too far away, falls into the red region, then null loses, and you accept alternative hypothesis. You can run it over and over again. And also you can visualize the probability value method, type 1 error versus type 2 error. All right, and that's a bit too hard, so let's not discuss that too much. Here's a visualization of two-tail test. Far away from the null, then null loses. Close enough to the null, then null wins. And far away could be either direction, left or right. This is rare. So let's stick to one-tail test. Okay, let's go to this example problem. The density of the Earth is known to be about 5.517 grams per cubic centimeters. Henry Cavendish, an English chemist and physicist, was the first scientist to accurately measure the density of the Earth. Here's a data set based upon his experiments conducted in 1798. Here's the data, and then the mean of this data and the standard deviation of this data are 5.44793 and 0.2 to 0.946 respectively. Okay, all right. Those are coming from the sample. These are sample statistics. And apparently 5.447, that's a bit less than 5.517. So make appropriate hypothesis. It looks like the mean of Cavendish's data is significantly less than today's recognized data, or maybe not close enough, I don't know. Let's set up hypothesis and test it using the significance level of 0.05. Okay, all right, let us go ahead and do that. First, let's set up the hypotheses. What's a null hypothesis? Mu is equal to what? Is it 5.517 or is it 5.44793? It should be well, this is sample statistics that we actually did, all right. Hypothesis, they revolve on the null value, which did not come from the sample, all right. Null means no, nothing, none. So it must have nothing to do with the sample. So you should not be using 5.44793. You have to use the other number, this one, 5.517. That's the null value. And with respect to the null value, you have to draw. Okay, there you go. And let's see. Less than today's recognized figure. So shade to the left. Make sense? And then let's find out critical value x. Okay, how do you do that? Well, n minus n2 over sc, you can do that. And then that's associated to t-score of 5% here. Recall that? Recall the t-table? Well, I'll leave that to you. N minus n2 over sc, if you do it right, the t-score should be negative 1.701. I'll leave that to you. By now, everybody must have used t-table many a times, so everybody must know how to do it. So if you do your computation, you end up with, let's see, 5.44719. Whoa, very, very close, but still, the null value is close, but it's in the blue region. I mean, the sample mean, observed sample mean, is close enough, but it's in the blue region. So I'll say accept null hypothesis and reject alternative hypothesis. Actually, this is a bit too close for comfort, to tell the truth. 5%, let's go down to about 2%. Then it looks like this. Yeah, a bit further down. And then this computation will be affected. And instead of 5%, you have to go to 2%. So in the t-table, let's see, where's the t-table? Degree of freedom is 28, and then let's look up 2%, not 5%. Yeah, 2% here. And 2.154. 2.154. 2.154. Was it 2.145 or 2.154? 28, 2.154. All right, okay, all right. And the y left, I mean y negative, that's because it's left here. So this one changes into 2.154. And if you calculate all that, and then punch into calculator, you're going to get, okay, all right. I'm far more comfortable. And the final picture here will end up being a little bit more comfortable. So this observed mean by Henry Cavendish in 1798 is now a little bit more comfortably inside this blue region. So if you use the level of significance as 2% instead of 5%, then you can say that this Cavendish experiment is not really biased to the left. It is very, very accurate considering that it was done in 1798 actually. If you use 5%, it was very, very close, so actually a bit too close for my comfort. But the same thing works actually. Okay, that is the critical value approach, and let's consider the probability value method just a little bit. Okay, sample statistics, all right. Hypotheses, okay, all right. Initial picture is like this. 5.517, 5.448, and we have to find out this probability. And how do you find it? Calculate the t-score, come like this. And how in the world are you going to calculate this p-value? Because if you look up the t-table, there's no way you can calculate the probability for general t-score. Is there a table like that? Yes, there is a table like that, but that's very crude, so you cannot make appropriate computation or appropriate decision like that. It's somewhere in the appendix of our textbook, but it's nearly unusable. Now, if you use Statistical Calculator, which is available in many web-based calculation tools, then you can calculate it, but still not a good way to do it. It's cumbersome. But assuming you went through all the obstacles, then you can still get it done. P is greater than alpha, so let's go with H0, like this. Does it work well? Well, in practice, not really. This probability value method works great for z-curves, but for t-curves, it's hard to apply. Another way is to find out the confidence interval. You see, from the sample statistic and hypothesis, they are the same, and find out the confidence interval, one-sided confidence interval, and looking for upper confidence bound. You see here now centered at 5.448, the observed mean, and then find out this upper confidence bound, and where is that mu value of 5.517 located? Blue region or red region? That's something we have done before. Back in lesson 11a, and also part of lesson 10, we did it. Doing all those computations, we get the upper confidence bound. Turned out 5.51781 something, very close but a little bit larger, so that 5.517 is within the confidence bound, so close enough to the null, so yes, works out. We go with the null hypothesis. A bit difficult method, but it works out, and it's based upon the method we used before in section 11a, or I mean lesson 11a. In any case, you can do it. Which method do I prefer the most? Of course, I prefer the critical value method. Students usually score the best for critical value method. That's why I did that one first. And that's why I'm emphasizing that one more than anything else. So in conclusion, the probability value method, which works so well for the z-curve, doesn't really work well for t-curves. So please beware.